In this segment, we look at some first-order logic proofs involving equality. The results are simple and the proofs are short. However, they illustrate our two new rules of inference and a couple of important issues. Let's start with a particularly easy case. Suppose we know that B equals A and we know that B equals C. Our job is to prove that A equals C. The proof in this case is particularly simple. It's just one step. We start with the two premises and apply equality elimination to derive the desired conclusion. The rule is shown here at the bottom. In this case, we let tau1 be B and tau2 be A. Phi here is the second equation, namely B equals C. The result of this case is phi with tau1 replaced by tau2. In this case, it means that B is replaced by A. The result is the sentence on line 3, namely A equals C, which is what we set out to prove. Now let's look at an example that's just slightly more interesting. Suppose we believe that f of A equals B and f of B equals A. Let's prove that f of A equals A. Again, the proof can be done in just one step. In this case, we let tau1 be f of A and tau2 be B. Phi here is the second equation, namely f of B equals A. The result in this case is phi with tau1 replaced by tau2, or vice versa. This time we use the equation in the opposite direction, replacing A by f of B. The result is this sentence on line 3, namely f of A equals A, which is, again, what we set out to prove. Now let's look at an example that illustrates how equational reasoning interacts with relational reasoning. We know that Pat's the father of Quincy. And we know that fathers are older than their children. Our job is to prove that Pat is older than Quincy. Proof goes as follows. We, as usual, start with our premises. The father of Quincy is Pat. And fathers are older than their children. Next, we use universal elimination to instantiate our quantified sentence. The father of Quincy is older than Quincy. Finally, we use equality elimination to replace father of Quincy with Pat, and thereby derive the conclusion that Pat is older than Quincy. Finally, let's work through an example involving a disjunction of equations. We know that P of A is true, and P of B is true. And suppose we know that A equals C or B equals C is true, but we're not sure which or whether both may be true. Our job is to prove that P equals C in any case. As always, we start with our premises, P of A, P of B, A equals C, or B equals C. On line 4, we start a new subproof with the assumption that A equals C is true. From this assumption and our first premise, we conclude that P of C must be true. Now, although that is what we intended to do, we're not done since we have proved the result only under the assumption that A equals C. We make this clear with the use of implication introduction to derive the sentence A equals C implies P of C. Now we start another subproof, this time with the assumption B equals C. As before, we derive P of C. And from this, we derive the implication B equals C implies P equals C. Now we have both A equals C implies P of C and B equals C implies P of C. Finally, we use OR elimination to combine our two partial results with our disjunction of equations. And we're done.